Hey there, this is Arnav from Pebble, and welcome back to the Introduction to Linear Algebra series. One of the main goals of linear algebra is to represent a vector space in terms of a very easy to write set of representatives. And so you might have seen, well, in previous videos we used set notation, where we would notate our space S, or we can also say V, and that would be a set of objects that were our vector space. But this could also mean this just means a set. It does not equal a vector space. This is not notation for that. So we need a notation or a way to simply represent a vector space very simply. But one of the main issues here is that, well, this vector space, the number of vectors is infinite in most of the cases that we have seen and will see. It is infinite. So usually vector spaces, the number is infinite, which means that, well, we can't write every vector out. So we can't have just a collection of a vector like 1, 0, and then 2, 0. We can't have a collection of vectors like this. This would not work. Okay, we can't do this infinitely until we get to infinity 0 or something. This will not work because of the vast amount of combinations that you could have with with bigger vectors. And so to solve this, we use something called linear independence, and I mentioned this term I mentioned this term earlier in the videos, but now we're actually just going to formally get into it. And what linear independence is going to help us do, it's going to help us find those representatives to characterize our entire vector space. And while this video won't go into the actual characterization, we'll set the baseline, which is linear independence, for how we do that. Okay, so what makes a set of vectors either linearly independent or linearly dependent, or linear independence and dependence? So a set of vectors, let's say v1, v2, v, and then all the way to v of n. This set of vectors, which belong to our vector space V, are going to be linearly dependent if there exist scalars such that C1 V1 plus C2 V2 plus ... plus Cn Vn equals 0, where not all of them are equal to 0. Okay, and we're gonna call that non-trivial. So trivial versus non-trivial. So our solutions to this equation need to be non-trivial. At least one of them has to be non-trivial. And trivial would mean that it equals 0, and then non-trivial would mean that it's not 0. And so if there exists a non-trivial solution to this, then that means that this would be linearly dependent. But let's say that C1 equals C2, which is going to equal all the vectors in between, which equals Cn, which is going to come out to be 0. If they all equal 0, which means they're all trivial solutions, we only have one trivial solution. This means that they are linearly independent vectors. And one way you can understand this graphically is that if I have a vector like this, and then I also have a vector like this, pretend those go through the same line. If I have these two vectors here, since I can make, by just doubling this first vector, I can make the second vector, that means that these are linearly dependent because some combination of this vector makes this other vector. Okay, so it's kind of like a line. They all have to not fall on the same line, or they all have to not be able to be created by the other vectors if we're thinking about it graphically. And so that's why we set it equal to 0. So if these can fall in the same line, then you would understand that this would be equal to 0. And then if they can't fall in the same line, something like just, I don't know, anything really, something like this. And if we got rid of this first vector here, then these two would be linearly independent because there's no possible way that we can use a multiple of this to get to this, basically. But if we were to add another vector like this, and we were to say, well, hey, if I have this vector, and then I add this vector, well, clearly there is some combination, because this goes horizontally, so maybe we could double this horizontally, and then add all of this, like this many times, do a lot of this, and we would get to this vector here. Okay? So that's how you would think about it graphically. So you think about it graphically. And so to test whether a given set of vectors is linearly independent, you need to first form this equation and then ask which values of our c's are going to satisfy this equation. And obviously, when they're all 0, it's going to work. But if this is the only set of values that would satisfy our equation, then they're linearly independent. And if there exists a set of values of c's that are not all 0, then the vectors can be, well, they are linearly dependent. Okay? So a couple of them can be 0, but just not all of them have to be 0. Okay, so let's take an example of a couple tuples. So we have this set of two tuples here. So 1 and 2, and then we also have 3 and 4. So these are in our set of two tuples, and we're going to see if these are linearly independent vectors. So let's set up our equation. C1 into 1, 2 plus C2 into 3, 4 equals 0. And to me, this clearly looks linearly independent, but for you, this might not be as clear. So if it's not as clear, then what you want to do is to multiply this out. So you're going to get C1 plus 2C1 plus, and we're going to put this in tuple, plus 3C2 plus 4C2, and that needs to equal 0. And so you can basically just add the first ones. So C1 plus 3C2, and then 2C1 plus 4C2. And then both of these need to equal 0 because the 0 vector is the same thing as because the 0 we have here is the same thing as a 0 tuple. And so once we have that, then we just need to check to make sure that we can do C1 AC2 equals 0, and then 2C1 plus 4C2 equals 0, and we need to solve these equations to find C. And clearly, because, well, this won't work, even no matter how you try to solve it, because you're doubling this here, but you're not doubling this. So if this was a 6, then yes, this would work. But since it's a 4, there's no scale factor that you can do to multiply both these equations just by trying to solve it normally. That would let you do it. So this means that C1, C2 both have to equal 0. So that's going to give us that they are linearly independent. And hopefully that example makes sense, because that's basically just the same bit of logic here. And we'll do one more with a set of column matrices, or rather vectors. So let's take 2, I need to write this bigger, 2, 6 minus 2, 3, 1, 2, and then 8, 16 minus 3. And once we have this and this set, we're basically just need to prove that, show if these are linearly independent or dependent. So same thing. And try this out. Try this out for yourself. And these are all in set of 3 tuples, by the way. So try this out for yourself. And then when you come back, I'm going to give you the answer and we'll talk about it. Okay, so hopefully you've had a chance to do that. And this is going to be linearly dependent. And the reason why is, hopefully if you take a look at this, what you're going to get is 2c1 plus 3c2. And basically what we're doing here is we're setting these equal to 0. Okay, so this is going to equal to 0, 0, 0. And you're just going across the line. So this is 2c1, 3c2, c3, c1, c1, c2, c2, c3, c3, and then that just has to equal 0. So each row has to equal 0 for it to be true. So 8c3 equals 0, then you're going to get that c6, c1 plus c2 plus 16 c3 equals 0, and then you're going to get that minus 2 plus minus 2c1 plus 2c2 minus 3c3 equals 0. And so once you have that, you can use Gaussian elimination, which we practice. So this is just the same thing, right? Instead of c1, c2, c3, we would normally use x, y, and z, but here we're just doing c1, c2, c3. So it's the same thing. So once you use Gaussian elimination, you should be getting that your solutions are c1 can be minus 2.5, c2 is just going to equal to minus c3, and so you can set them to, I don't know, really anything, I think. I believe this is what you would get. If it's not, correct me in the comments. But if it is, then you can get that c1 equals minus, oh, this should be c3. Okay, now it's right. So if we set c3 equal to something like 2, then we'd get c2 equals minus 2, and then c3 equals 2. And so with that, these are solutions, non-trivial solutions for our equation that we set up. So that means that this is linearly dependent. Linearly dependent. Okay, great. So that brings us to our first theorem. So this is basically just a finite set of vectors is going to be linearly dependent if and only if one of the vectors is a linear combination of the vectors that precede it in the ordering established by the listing of vectors in the set. So basically for this example, since you can make, just try this one out, but you can make this you can make this third vector using the first two, which is going to prove this theorem to you. Okay, and since you can, that means that this is going to be linearly dependent. So that's a quicker way to do it, I guess. And then for our second theorem, basically if you have a subset of your vector space V, and it only has a vector u. So we have a subset, and it's only u, and it belongs to V, and it's S. We're gonna call it S. So if S consists only of u, then it's linearly dependent if and only if u is equal to 0. Okay? Because, well, a vector, you can't, if you have a graphical vector here, right, like this one, well, unless it's 0, well, you can't multiply it to make itself by a non-trivial amount, basically. Okay, and the third theorem that we're going to talk about is that a subset of a vector space V consisting of two different vectors is linearly dependent if and only if one vector is a scalar multiple of another. So if you have two vectors in your set, like let's say 1 and 2 and 2 and 4, and these are your two vectors. These are your two vectors. These are linearly dependent if and only if one vector is a scalar multiple of the other. And you can see here, I did this easily, but the scale factor is going to be 2. So multiplying this one by 2 gives you this one. So that means that they are linearly dependent. Okay, and this makes sense because they lie on the same, graphically they will lie on the same line. So it makes full sense that they're linearly dependent because they're on the same line. Okay? And a lot of the time with linear independence, graphing it does help if you have like graphing it does help in a lot of cases, but you won't always have the luxury to graph it, so be comfortable using the equations. Okay, and the next theorem is that if you have a set of vectors and inside that set, so let's take a set like this one, okay, and I'm just going to change this to 5 just to make these linearly independent. If you have the 0 vector inside your set, then this is automatically going to be linearly dependent. And this is because, well, you can, even if these two have to equal 0, the coefficient, this one can be anything, right? So this could be any n, and you're still going to get a 0 out of it. So because remember we define linear dependence as if there's any non-trivial, they don't all have to be non-trivial, but just one of them has to be non-trivial. And because one of them is non-trivial, that means that we are linearly dependent in this case here. Okay, and then the fifth theorem that we want to talk about is if a set of vectors S in a vector space is linearly independent, then any subset of S is linearly independent. So this just makes sense because, well, this just makes sense because, well, if you have like vectors like this, and I'm not putting the square brackets, but yeah, actually I'll put them, but it's fine. This is if you have these three vectors, right? If you take a subset, any subset you take, so if I take this subset or if I take this subset, well, that's going to be linearly independent because these three are already linearly independent. So since you can't, linearly independent means that you can't make any of the vectors from any of the vectors. So because that's true, then obviously even if you pick any two, cherry pick, it's not going to hold true. And then the last theorem that I want to talk about is that if a set of vectors S that belong to V, our vector space, is linearly independent, then any linearly dependent, then any larger set containing S is also linearly dependent. Okay, so if you have S that such that it belongs to V, and then you have W and S belongs to W as well, and W belongs to V. If S is dependent, then that means W is also going to be dependent. That's basically just the theorem. And this is one of the proofs that I'll let you off to try because I find it very interesting. So good luck with that, and I'll see you in the next video.